Hello everyone. We present I2SDF, a holistic neural SDF-based framework for complex indoor scenes that jointly recovers the underlying shape, radiance, and material fields from multi-view images. The decomposed results can be used for varying applications, including novel view synthesis, 3D reconstruction, scene editing, and relighting. Our contributions include: firstly, we managed to precisely reconstruct fine-grained small objects inside the scene, where previous methods failed. Secondly, we introduce a holistic intrinsic decomposition framework using Monte Carlo Raytracing technique to enable photorealistic indoor scene relighting and editing. Thirdly, we provide a high-quality multi-view indoor scene synthetic dataset with ground truth camera pose, geometry, and material annotations. Here is a preview of 3 example scenes in our dataset. Neural radiance fields have achieved promising scene reconstruction results in recent years. In particular, NUS and VOL SDF use neural sign distance fields to represent scene geometry and use volume rendering to render colors into an image. Our method adopts VOL SDF scheme as the neural representation backbone. However, for complex indoor scenes, it is insufficient to achieve plausible 3D reconstructions from RGB loss only. Recent methods such as Mono SDF incorporate additional geometry priors, including depths and normals for better reconstruction quality. Our method also exploits depth and normal priors to guide network optimization. We now show the overall pipeline of our method, which consists of the neural sign distance field, neural radiance field, neural material fields and emission field, and finally the Monte Carlo rendering layer, which uses the decomposed factors to re-render the scene image. We'll introduce them respectively. We first introduce the geometry and radiance fields. We optimize the networks by minimizing the losses between the volume-rendered RGB, depths, normals, and ground truths. However, even with dense geometry priors, SDF-based methods like Mono SDF still fail in reconstructing thin objects like poles and chair legs. We analyze that the failure to recover small objects can be attributed to the vanishing gradient problem. In an indoor scene, the neural network tends to converge faster in low-frequency large objects like walls and ceilings than high-frequency details, as shown in the top left figures. However, we observe the fact that the gradient of volume density sigma with respect to SDF value d decays exponentially with the increasing d. We illustrate an example of vanishing gradients in the bottom left image, where the dotted lines denote the missing small object. We visualize the gradients in blue, and the gradients for points near the object off the surface are almost zero, so the thin object can hardly be recovered by gradient descents. To address this, we propose to insert bubbles for the missing surface points to create gradients for the SDF. As shown in the bottom middle and right images, the inserted bubbles create many local surface islands near the thin structures, allowing the growing up of the missing small object. We show an example of how our bubbles gradually optimize the missing chandelier in the top figures. Specifically, the bubble points are obtained by back-projecting depth images into 3D space according to the camera poses and intrinsics. We define bubble loss to minimize the absolute SDF values of these bubble points to create local surfaces. Next, we'll introduce how our pipeline decomposes lighting. Different from single-object scenarios, indoor scene images are usually captured from the inside out, and most lighting information has already presented inside the room. Therefore, we can directly predict indirect illuminations from the aforementioned radiance field. However, since the radiance field is trained from LDR images, the light intensity from emitters is usually underestimated. Therefore, we add a neural emitter semantic field into our pipeline to explicitly determine whether a 3D point is on an emitter. As shown on the right, we supervise the emitter semantic field by ground truth emitter masks. After the emitter semantic field is trained, we cluster the emitter points as K emitters, and assign a learnable emission value for each individual emitter. Then, we'll introduce the neural material field in our pipeline. We use GGX microfacet material model to present scene material and add MLPs to predict the surface diffuse albedo, specular albedo, and roughness. With the decomposed lighting and material, we finally introduce the differentiable Monte Carlo rendering layer using Raytracing to re-render the scene image. Our rendering algorithm mimics the path tracing algorithm in traditional rendering. Firstly, we trace the primary ray from the camera to intersect with the neural SD field. The intersection point S can be estimated by the volume rendered depth. Then, according to the predicted normal and material parameters at S, we can importance sample n secondary rays starting from S by the GGX probability distribution. We predict the incident radiance value of each secondary ray, which is divided into two cases. If the ray hits an emitter, we directly retrieve the emission value; otherwise, we predict the radiance value by the neural radiance field. Finally, the surface color can be rendered by the Monte Carlo integration of BRDF values and incident lighting. We jointly optimize the parameters of material networks and the learnable emission values by minimizing the rendering loss. Our Monte Carlo rendering layer can easily perform scene editing and relighting by modifying the corresponding input material or lighting values. Now, we'll present some experimental results of our method. Firstly, we show the reconstructed geometry by our method. We demonstrate the reconstructed normal maps in moving views. Note that our method reconstruct the chandelier where mono SDF fails. Next, we present results of novel view synthesis. For baseline methods, mono SDF fails to render thin structures, while instant NGP suffers from overfitting to training views, causing severe artifacts in novel views. We also present novel view synthesis results in real data. Our method also achieves superior quality. Finally, we present scene editing and relighting results powered by our physically based renderer. We can edit textures on the object surface. We can insert an virtual object into the scene with photorealistic reflections and shadows. By adjusting the roughness, we can change a diffuse surface into a mirror. We can turn on the lamp and further adjust the brightness and emission color. Our code and data will be available at our project page. Thank you for your listening.